All right, today we're diving into a field of science that has this incredible, almost magical trick up its sleeve. It's called statistical mechanics, and really it's all about finding these simple, elegant answers that are hiding in plain sight, right inside of what looks like total chaos. So, let's start with the big question, the one that kicks this whole thing off. What do you do when a problem is just, well, too big, too messy, with way too many moving parts to ever hope to solve by looking at each piece one by one? That question isn't just some philosophical thought experiment. It's a very real wall that scientists run into all the time. The truth is, some calculations are, for all practical purposes, completely and utterly impossible. I mean, think about a simple block of ice. You look at it and think, okay, it's just frozen water. But inside that block, there are trillions upon trillions of water molecules, all vibrating, all interacting with each other. Trying to write down, let alone solve, the equations for every single one of them? No way. Forget about it. Or let's think bigger. Picture an earthquake fault line. It's just jam-packed with countless rocks and boulders of all sizes. Predicting exactly how each one is going to shift and grind against its neighbor during a tremor, that is a mind-bogglingly difficult task. And this isn't some old, dusty problem from 100 years ago. It's happening right now, all around us. The internet, for example, has billions of nodes, computers, routers, servers. Trying to analyze the exact state of all of them at the exact same time is a total computational nightmare. So the crucial point here is that a direct, piece-by-piece approach is often, as the saying goes, simply infeasible. But, and this is the paradox, a block of ice melts at a very predictable temperature. Earthquakes tend to follow certain patterns, and the internet, for the most part, actually works. So how do these unbelievably complex systems end up showing such simple, predictable behavior? Well, this brings us to the absolute genius at the heart of statistical mechanics. The secret is, if you can't understand the individual, you just have to change your perspective. You have to look at the crowd. For instance, picture a single molecule just bouncing around inside a gas. It's following what physicists call a random walk. Its path is chaotic, it's jagged, and it's completely and utterly unpredictable. You could never guess where it's going to be a second from now. But now, what happens if we track thousands or millions of these molecules, all starting from the very same point? Suddenly, all that chaos just disappears. And what's left is this beautiful, clear, and perfectly predictable pattern that emerges from the crowd. That's the magic trick right there. And this brilliant idea, it has a name, the ensemble. So instead of trying to predict one impossible-to-track system, you just imagine a huge collection of similar systems. It's kind of like trying to predict millions of coin flips at once instead of just one. You then study their average behavior. And it's right there in that average that the simple, predictable laws just reveal themselves. So this really lays out two completely different ways of looking at the world. The microscopic view, it tries to follow one chaotic, irregular path, and it just gets lost in the weeds. But the statistical view, it steps back, it looks at the whole crowd, the ensemble, and all of a sudden it discovers simple, orderly, patterned laws. Once you adopt this study the crowd approach, it's like you've learned a whole new language for describing reality. It gives us an entirely new set of concepts and rules to work with. And the most famous of these concepts is probably entropy. Now, you've likely heard it called disorder, but it's actually much, much deeper than that. It's really a way of counting all the possible microscopic ways the individual parts can be arranged to give you the same big picture. It's a fundamental measure of information, really. So why does that matter? Well, because entropy is literally everywhere. The very same principle is used to figure out the best way to compress a JPEG file on your phone, and it's also used to describe the ultimate theoretical fate of the entire cosmos, the heat death of the universe. I mean, that is a staggering range of application. Another really powerful concept is phases. We all learn about solid, liquid, and gas in school, right? But what statistical mechanics reveals is that those are just three of literally hundreds of possible collective states that matter and other systems can organize themselves into. And the idea of a phase goes way, way beyond just water. It can describe bizarre things like quantum superfluids that flow without friction, the conditions right after the Big Bang, and it can even describe those earthquake faults we talked about, which can be in a pinned phase or a sliding phase. And really, the applications of thinking this way are truly universal. They stretch from the largest scales of the cosmos all the way down to the code that's running our entire world. In physics, this is bedrock stuff. It explains the difference between metals and insulators, how lasers work, what happens when stars collapse, and it even helps us decode that faint microwave echo of the Big Bang itself. In the world of technology, it's an absolute powerhouse. Engineers use these ideas to simulate traffic flow, design more efficient computer chips, run powerful Monte Carlo simulations, and build the very communication networks that connect our entire planet. And its reach just keeps on expanding. It's crucial in bioinformatics, in understanding the edge of chaos in all sorts of systems, and even in explaining social phenomena like the 6 degrees of separation that shows how we're all connected.
Which, of course, brings us right back to our central theme. This isn't really the science of complexity, it's the science of simplicity. It's all about finding the elegant, predictable rules that secretly govern our messy, complicated world.
This is it. This is the entire field in one sentence. Statistical mechanics explains the simple behavior of complex systems. The goal isn't to get bogged down in the complexity, it's to explain why, against all odds, simplicity so often wins out. At the end of the day, it all comes down to one powerful idea: emergence. This is the science of how order emerges from chaos, how simple rules emerge from bewildering numbers of interactions, and how predictability emerges from randomness, all by just having the wisdom to look at the crowd. And that kind of leaves us with a final thought to chew on. Think about the traffic jam on your commute, or the wild fluctuations of the stock market, or even just the buzz of a crowd at a concert. What incredible patterns might emerge if you just stopped focusing on that one car, or one trader, or one person, and started looking at the whole ensemble?